We're going to be looking today at going back over what you should have been looking at with simple harmonic motion. We're going to be looking at two very specific types of systems. We're going to be looking at a mass spring system. You need to take the earbud out of your ear, please. The mass spring system, and we're going to be looking at pendulums, simple pendulums, okay? You looked at both of those systems when you did the lab last week, okay? So this should not be new looking to you. And the factors that sort of affect those systems, okay? All right, so first system we're going to look at is a pendulum. All right, if you talk about a pendulum, what is a pendulum? When we talk about a pendulum, we've got a mass. It's going to be attached to a massless spring, and it swings about a vertical equilibrium position. When we say vertical, we mean this, right here. Yes, it is a mass hanging on a string from a pivot. Equilibrium is when it's straight down, okay? Think about it. That's the 0 point. If you left it alone, that's where it would rest. That's what we consider the equilibrium point. So what are we going to do with this thing? If we've got it here, we're going to pull it back, right, to some angle, and we're going to let it go. Now, the thing I need you to know is that there is a restoring force, just like there is in any simple harmonic system. Gravity is the restoring force in this case, isn't it? Gravity wants to take it when we put it back here. Gravity is the thing that makes that mass go back down to equilibrium, isn't it? It continues to have energy, though, so it goes back up and down and through that system again, okay? When we talk about the period of a pendulum, we are talking about if we start by pulling it back, one entire period is where it goes back through equilibrium up to the equilibrium point and back to its beginning again. Does everybody get that? One period is where it starts and goes back to start. So that's 4 separate sections, isn't it? From where we pull back to equilibrium, from equilibrium to how high it goes, from that point back to equilibrium, and then back to where we started. So 4 different sections, and you can see those on your chart. All right? So remember, though, something you need to know about pendulum systems in particular. Pendulum systems are only considered simple harmonic motion for very small angles. So if we pull back in real life to 60 degrees, it's not really a simple harmonic system. It's not going to keep going all the way back to 60 degrees, is it? Very quickly, it'll dampen down. So what we notice is this. Small amplitudes, that is less than 20 degrees or so, okay? So if we pull it back just a little bit and it rocks back and forth, it displays simple harmonic motion, all right? Anything more than 20 degrees and it's out of the question, all right? So let's look at what this does. So we're going to start with the initial position here at t equals 0, all right? Now, if you look at this, this is its maximum displacement, isn't it? That's what this is. This is displacement. This, of course, is velocity. We've got acceleration, right? Kinetic energy and potential energy. So its displacement at t equals 0 is the most it's going to get to the right, isn't it? So this is going to be x sub 1, and this is the max displacement to the right. Now, we've pulled it back here. What is its velocity at this point before we let it go? 0, isn't it? So at its max displacement, its velocity is 0. So this is v sub 1 equals 0. As a matter of fact, I need you to understand that the velocity is going to be 0 every time this thing switches what? Direction, yeah. Every time it switches direction. Now, the acceleration. What's acting on this thing? Gravity. And it's at its maximum, isn't it? Okay, so it's going to be acting right here. So this is the max, and it is to the left. If this thing is displaced to the right, what direction does it want to go? It wants to go to the left, doesn't it? So that's the direction the acceleration is in. All right? Kinetic energy. If this thing is not moving here, what's its kinetic energy? 0. What about its potential energy? It's at its maximum, isn't it? Because it's at its highest point right here, isn't it? It's mgh, isn't it? Okay, so potential energy is at a max. All right, so now we're at the bottom point. This is equilibrium, isn't it? So this is T sub 2, and this is the period, which is big T, divided by 4. Does everybody understand that? 4 sections. Remember? 1, 2, 3, 4. All right, so what is its displacement at equilibrium? 0, isn't it? What's its velocity? It's at its maximum, isn't it? As it goes through here, how do we know it's at its maximum? Yeah, because the potential energy has gone to what? 0, hasn't it? And we've got this exchange between kinetic and potential, haven't we? So if all of the potential now has gone to kinetic, that means all of the mgh now becomes 1/2 mv squared, doesn't it? So yes, velocity is at the max. Okay? What direction is the velocity? Yeah. So it's to the left. Acceleration, though.
Isn't acceleration
At 0 because it's switching?
Yes, it is switching direction, so the acceleration is 0. Kinetic energy. Yep. And potential energy is 0. Now we're at T sub 3, which is the period divided by 2, isn't it? Big T is period. So now we are displacement. Our displacement is the max to where? Yeah. Max to the left. Velocity is what now? 0, because it's doing what? Switching directions. So every time it switches directions, your velocity or acceleration is going to go to what? 0. All right, now acceleration this time is going to be what? Yep. Max to the right. You get the idea. Kinetic energy, though. If the velocity is 0, the kinetic energy is 0, and potential energy is at a max. So you see what's happening between these two, don't you? All right, so now we're at T sub 4. We're back at equilibrium. This is what? 3T over 4, right? It's 3/4 of the way, isn't it? All right, so what about my displacement again? 0, it's at equilibrium, isn't it? Velocity? Yep, max to the right. Acceleration? 0, because it's changing directions. Kinetic energy is at a max, and potential energy is at 0. And then finally, we're at T sub 5, which is total period. We've done one cycle. So we know what's going to happen here. We know its displacement is what? Max to the what? Max to the right. So we're starting all over again, basically, aren't we? Velocity is what? 0. Acceleration? Yep. Max to the left. Kinetic energy? And potential energy? Max. Okay. So we understand the rhythm of this pendulum, don't we? You need to be able to describe what's happening in a pendulum system. All right, so let's talk about the period of a pendulum down here. What is the period of a pendulum? What did we say it is? It's one full what?
going and back.
Yep, one full cycle. Yep, back to beginning. So we can say from max displacement and back again, right? Now, the period is dependent on two things. It is dependent on the length of the pendulum, L. In other words, dependent on the length of the string. You saw that in your lab, didn't you? The longer the string was, the longer the period, right? Doesn't that make sense? It's also dependent on gravity. If you took a pendulum that had a certain period on Earth and you took it to the moon, what do you know about the gravity on the moon? It's less, isn't it? Acts less, it's 1/6 of. So what's going to happen is it's going to change the period of that. Even at the same length string, it's going to change the period of that pendulum. It's actually going to make it faster. The less gravity you have, the faster it'll tick-tock. I know, seems sort of wrong, doesn't it? But this is why. As we have t, here's the formula. 2 pi. Guess why there's a 2 pi in there? What do we notice about this? It's kind of circular, isn't it? It's part of an arc, isn't it? Okay? 2 pi times the square root of L divided by G. So the smaller G gets, the bigger the period gets, doesn't it? Because it's in the bottom. This is an important formula for you to know. And if you look on your, look right here, on your formula sheet, you will see it in the second column under mechanics, T sub P. That is T for the period for pendulum, 2 pi over L divided, square root of L divided by G. So it is on your formula sheet. You don't have to memorize this one. All right, so how are we doing so far? We're going to now use this to solve some problems. To your information here, units is seconds. Okay? Think about it. This is meters. This is meters per what? Second squared. So we end up with second squared. Square root of that is just seconds, isn't it? So let's look at solving problems, things that you're going to be doing today. Example A. It says the acceleration due to gravity on the moon is 1/6 that of the Earth. You told me that already. The period of a pendulum on the moon is measured to be 7.6 seconds. We want to find the period of the pendulum on Earth. Now, what did we say? The lower gravity got, the faster it got. So what are we expecting? If we know it's 7.6 seconds on the moon, what are we expecting to see on Earth? A period that's longer or shorter? Shorter. If the gravity gets smaller on the moon, then the period is faster, isn't it? So if we go to gravity on Earth, which is bigger, the period should what? Slow down, shouldn't it? So we expect to see the period slow down. So keep that in mind. So if you get an answer, you see how if you understand that relationship, if you got the wrong answer, you'd know it pretty quick, wouldn't you? If you got something that was faster, you'd be like, well, I did something wrong here. That shouldn't happen. Okay, so let's figure out how to do this. We know we're going to have to use this formula, don't we? 2 pi divided by square root of what? L over G? Only problem is there's two things here we don't know. We don't know the period on Earth, but we also don't know L, do we? How do we find the period if we don't know L?
We can know it by figuring out the moon.
Yeah, we could use the moon system first. Does everybody see that? If you can't get it through Earth, you can get it through the moon. So let's start with the moon. So if we start on the moon, we could find the period by saying we know the moon is equal to 2 pi square root of L divided by, instead of G, G is what? It's G over what? G over 6. All right, cool. So let's find this. All we have to do is plug in. We know the period is 7.6, and it's always in seconds, by the way. If you're dealing with period, it's in seconds. If you want to go back and add its work out. All right, so 7.6 equals 2 pi times the square root of L, and this is 10 over 6, isn't it? So how do we solve this for L? What's the first thing we're going to have to do? Divide by 2 pi. So let's do those. We're going to divide both sides by 2 pi. That goes away. Now what? Square. So we're going to square both sides now. So this and this will go away. And then what do we do last? Multiply both sides by what? Yep. Multiply both sides by 10 over 6. That'll go away. So 10 over 6. So now we've got L on this side, and we can work out what's left on this other side, can't we? You should get approximately 2.44 meters. Make sure you work that out on your calculator and know. 10 times 7.6 squared divided by 6 divided by 4 divided by pi squared, right? Do you see where everybody always makes the mistake? They forget to square. So you might want to put this in first, divide and then square it, and then multiply by 10 over 6. You need a calculator, they're up here. All right, so now we have L. Did everybody manage to get 2.44 meters? Okay, so now we can do what? Plug it back into the formula for Earth. Y'all are getting to be better problem solvers. The fact that you even thought about the fact that, hey, I've got this stuff for the moon and I can do that first to get the piece I don't know is serious progress, right? We're learning to do multi-step problem solving. So T is now 2 pi divided by 2.44 over what this time? Just 10. So this becomes an easy problem, doesn't it? And see what you get. Is it bigger than 7.6 or is it smaller than 7.6?
Smaller.
Yeah, it is. It should be smaller. What'd you get?
I'm still trying to get 2.44.
Okay. Take 7.6 and divide it by 2 pi and hit enter. Did you get that? Now square that. Now multiply by 10 and divide by 6.
7.6 divided by 2 pi squared.
Hit enter and then square that.
Squared.
Divide by 6, yeah. You should be 2.44.
I got
Okay,
hundreds.
hold on.
I got 3.103.
Hold on. 7.6 divided by 2, enter, divided by, I bet you multiplied, you said divided by and then did 2 pi, didn't you? You know what your calculator did? It divided by 2 and then multiplied by pi. Hit divided by 2 and then hit divided by pi. Now square it and multiply by 10 and divide by 6. Remember your calculator does, yeah, I got 2.44. That's where your mistake was. You've got to be very careful with order of operations. It does exactly what you tell it to do. And if you do 7.6 divided by 2 times pi, remember it does left to right. Multiplication and division are the same. So it divided by 2 and then multiplied by pi, which just threw you off. You were off by at least a factor of 3. All right, so are we good now? Okay, so you should have gotten 3 point what?
3.1037. 3.10.
Okay, so 3.10 seconds. Okay, so let's look at example B. That is less, isn't it?
Why is it less? I thought it
That
was
means
supposed to
it's
be
going
longer.
faster, technically.
Yeah.
Not on Earth.
No, that is.
Yeah. Remember, it gets longer on the moon, but we're going backwards to more gravity. So if we went backwards from less gravity, because remember we had the period for less gravity, didn't we? And if we have, as gravity goes down, the period goes up. So as gravity goes up from the moon to the Earth, then the period should go down. And if you look at it right here, as this number gets bigger, this whole expression right here gets smaller, doesn't it? That's why. So you got to think about it. Which way are we going? We're going the opposite direction of what we said. Our gravity is actually getting bigger because we're going to the Earth, which means our period should have gotten shorter. And it did. Period got shorter. Gravity went up, so T went down. That's our relationship, right? And opposite. All right, so let's look at example B. We have a 0.5 kilogram mass suspended from a 40 centimeter string, creating a simple pendulum. The mass is displaced at an angle of 15 degrees. What is this telling me? It told me it's displaced at an angle 15 degrees. It's telling me I can treat it like a what?
Like a perfect
Simple harmonic motion.
Simple harmonic oscillator, right? SHM. That's what this is saying. So we can treat it like SHM, which means we can use that formula, can't we? All of the things that we see. It says calculate the following. Calculate the frequency of the pendulum. So one of the things you need to know is, what is the formula for frequency? What is that relationship? So frequency, here's another formula you need to know, is 1 over period. Okay? That is something you need to know. And that, unfortunately, is not on your formula sheet. Actually, it is. I'm sorry. It is. It says T equals 1 over F. So that's on your formula sheet as well. So this you also know. It's the second down in the second column. If you need to see where almost all the formulas we're using in this unit are at the bottom and in the second column. Okay? All right. So calculate the frequency. If we want to calculate frequency, all we need to do is find the what? Period. And then take the reciprocal. Right? So let's start by finding the period. So the period is going to be 2 pi divided by the square root of L over G. So this is 2 pi. What was the length of the string? Hi. Guys, what was the length of the string?
40 centimeters.
Okay, so first place you'll make a mistake, right? Do we put 40 in this problem?
Nope.
What do we put in this problem?
0.04.
No, that would be 4 centimeters. 0.4. 0.4 divided by what? What planet are we on? Earth. 10. So we're going to get the period, and the period is what? Point 0.4 divided by 10. Take the square root. Nope. Times 2 times, I'll do that a little bit. 1.26. So this is about 1.26 seconds, which means now we can find our frequency by doing what? 1 over the period, right? So 1 over 1.26. All you have to do is hit the x to the negative 1 button on your calculator and hit enter. You should get about point what?
795.
So about 0.80. And this is seconds to the negative 1. We have a unit for that. Seconds to the negative 1 is hertz. So seconds to the negative 1 is equal to what we call Hz, which is hertz. H-E-R-T-Z. Hz is the short of it, okay? So we would say this is 0.80 seconds to the negative 1, or 0.80 hertz, okay? If you listen to sound, it's hertz, okay? Is everybody good so far? Now in part B, it says calculate the height of the pendulum above the equilibrium position when it reaches its maximum displacement. This is a very typical problem that everybody always freaks out about. And there's no reason for it. Let's draw this picture. What do we know? Typically we have a mass right here, don't we? Yes? This is L. Now we want to max displace it out here. This is also still L, but here's the thing. I want you to notice something. This is where it originally started. This is where it ends up. It's asking us for this. Does everybody see that? Yes? No?
Yep.
Okay. So, we have to work this problem. This is a right triangle. Guess what, guys? And we know this angle right here, don't we? Didn't it give us that angle? It said it displaced it how many degrees? 15 degrees. Okay. So we know that angle right there. If this is a right triangle and L is the hypotenuse, can't we find this chunk right here in green? What would that chunk be?
That'd be cosine.
L cosine theta, wouldn't it? Do you agree? So if this whole thing from here to here is L, but this chunk right here is L cosine theta, I want this chunk right here. So how do I find this chunk right here?
We just take L cosine theta and subtract it from 40, since that's what L was.
I take L and I subtract L cosine theta from it, don't I? Do you see how you find this problem? Do we know all of those things? Do we know L? Yes. Do we know theta? So this is actually a fairly straightforward problem, isn't it? If you know trig. So L is 0.4 minus 0.4 times the cosine of how many degrees? So our distance above is what?
0.0136.
Okay, so 0.14 meters. So it's about 14 centimeters above where its lowest point is, isn't it? So at 15 degrees, we've pulled it up. All right? It says also draw the free body diagram of the mass at this point. Did we draw our free body diagram? We should do that. FBD. All right, so here's my mass. What, at this point right here, when it's pulled all the way back at this point right here, what is acting on it? What forces are acting on it?
Gravity.
Okay, so gravity's straight down, so we got mg here. What else?
Does it have to be a tension force?
Yes, it's connected to a string, so it has to be a tension force this way, doesn't it? Is there anything else acting on this? What? I can't think of anything, can you? No. It's not in motion. It's just sitting there. So no. That's it. All right, so now it says now draw the free body diagram of the mass at the equilibrium position. So free body diagram, it's now at equilibrium, which means it's straight down, doesn't it? So what is my free body diagram of my mass at this point? mg straight down and tension straight up. And what do you know about those two amounts? They should be equal, shouldn't they? Yeah. They should cancel out. So if it says find the tension in the string at this point. If we're going to find the tension in the string,
What's the tension equals gravity and force of gravity is
here's the problem though. What else is at play? This thing is moving in a what?
oh, it's moving.
Well, I mean, if it's going back and forth, as it passes through the equilibrium position, it's in a circular motion, isn't it? Oh, it's in circular motion, isn't it?
There has to be some sort of acceleration.
Centripetal acceleration, isn't there? It's circular. So we have to do what? Newton. So if it's sitting still, tension is equal to mg. But if it's motion, if it's rocking, if it's in motion, we know the sum of the forces, which is equal to ma sub c, isn't it? Remember Newton? Except we don't know a. What do we know?
We have R.
mv squared over r, but r in this case is what?
The length of the string.
Length of the string, yeah. So this is going to be mv squared over L equals, what's going up towards the pivot? Tension minus, because it's going in the opposite direction,
Gravity.
mg. Yes. So if we want tension, we got to solve for T. T is equal to what?
mv squared over L plus mg.
Yes. mv squared over L plus, I got a problem though. What do I not know in this?
Velocity.
I don't know the velocity. Is there any way I can figure out the velocity? Sure enough, there is.
Potential.
Energy! Yes! You are on fire today. So to find the velocity, we do energy, don't we? If this is conservative system, mechanical energy initial equals mechanical energy final. And what is the initial mechanical energy? mgh. And that's equal to 1/2 mv squared, isn't it? We don't even need the mass right here. So we know the velocity. We've done this problem a bunch of times. The velocity, isn't it equal to square root of 2gh? Haven't we seen that formula over and over and over again? We've solved for this a couple of times. You solved for it in your test when we did energy. So let's plug in. So what is the velocity at the bottom there? This only works because we're looking for the velocity at that bottom point, aren't we? So what is it? Square root of 2 times 10 times, didn't we find h? Didn't we just figure out what h was? That's 0.14. So what is my velocity? Let's figure it out. 2 times 10 times 0.14, take the square root of that sucker, and we get what? 1.6?
Wasn't it
It was 0.01.
Yeah,
It was
0.014.
1.3637.
Oh, 0.014, excuse me. 0.014, you are correct. So 0.014. So 0.53. So 0.53 meters per second, which we can now plug into what? So we have 0.5 kilograms, right? So let's finish this up. 0.5 times 0.53 squared divided by what? 0.014. 0.5 times 10. So the tension. Be very careful here. Have you noticed when I do period, I'm doing the little bars on the side of the T? That's different than T, which is tension, right? Be careful when you draw period and you don't confuse period and tension. It's a little tough sometimes. Okay, so what is tension?
5.34.
5.34 what?
1.
Okay, 5.34 what? Units, please.
Newtons.
Newtons. Okay. Describe one modification to double the period of the oscillation. So if I want to double the period, let's go back to our period formula. 2 pi times the square root of L over G. What is the easiest way to make the period get longer? Quadruple the length. Why quadruple the length? Because you're taking the square root, aren't you? So we want to take, and we want this to be doubled, right? So we want 2 times this, which means if we want to put it in up underneath here, we need it to be 2 pi times the square root of 4L over G, don't we? So we want to quadruple the length of the string. Now, some of you might be tempted to say we make gravity less. Is that reasonable? Is there any way to make gravity change on Earth?
We can if we try.
Yeah, no. If you figure that out, you could make a lot of money, okay? All right, so let's keep going. We've done pendulums now, correct? So does everybody understand how a pendulum system works? How the length of the string and how gravity can affect it. You know how to find the period, you know how to find the frequency, and what that relationship is. So I'm going to get into mass spring systems. This is the other major type of simple harmonic motion. So let's look at these. See what we got here. If an object moves repeatedly over the same path in equal intervals of time, that is a simple harmonic oscillator, okay? Those movements are called oscillations. If the periodic motion is directed towards an equilibrium position, the motion is simple harmonic motion. What that means is it stretches out and goes back through the equilibrium point, back and forth, back and forth, back and forth, over and over again, right? Do you see that this is the same thing as the pendulum, only it's not doing this? Think about it. We pull it out, don't we? So right here, we're at maximum extension, aren't we? One period is to go from here back through to here again. That's 1, 2, 3, 4. This is the exact same motion as the pendulum, isn't it? Only it's linear instead of two-dimensional. Same places, same behavior. No kinetic energy, no velocity. All potential. But instead of gravitational, it's now what? Spring. 1/2 kx squared, right? So we go from that max to maximum kinetic energy and velocity to max spring energy to max kinetic to max spring to max kinetic to max spring to max kinetic. And every time it changes direction, what happens right here where it's going from one side to the other, what happens to the acceleration at this point? It goes to 0, doesn't it? Okay? All right. We have changes in acceleration here and here, don't we? I want you to think about why there's acceleration. You know there's no velocity, don't you? Why does there have, if there's no velocity, why does there have to be acceleration? Because it's switching directions. It's slowing down rapidly, isn't it? If you've got the velocity slowing down, that means the acceleration has to be happening, but because it's slowing down, it has to be in the opposite direction of motion, doesn't it? Which is why at those ends, the acceleration, if it's going this way, the acceleration is going this way, isn't it? So we've got that relationship happening there. No acceleration here. Okay? At that exact point. So let's go through and let's figure out what we got else got going on here. If an object undergoes simple harmonic motion, two characteristics. The force is directed towards what? Okay, what do we call that? Yep. It has a restoring force. That is what? Proportional. It's proportional to the distance from the equilibrium point. Remember, F is equal to what here? Kx, right? Or really negative Kx. If you look on your formula sheet, it's negative Kx. That means it's in the opposite direction. The force is in the opposite direction of the motion, right? If we pulled it back here, it wants to push it back this way towards equilibrium, doesn't it? So it's the opposite direction. It is proportional to the distance from equilibrium.
Just proportion, is it like different for different simple harmonic oscillators? For the spring, would it be different from the pendulum?
Yes, different formula. Well, it's moving circularly. This is moving linearly. We can't use linear formulas with something that's doing this, can we? Okay. So, example A. Why does a pendulum only approximate simple harmonic motion? What is the restoring force? Yeah. And is gravity acting towards equilibrium? What's the direction gravity always acts in? Downward. So it is not acting. Look at this form. Well, we don't see it here, but you could, if you looked at it this way, you've got this guy right here, but your restoring force, which is gravity, is only acting downward. So the problem is equilibrium is this way. So do you see why it doesn't act exactly as a perfect simple harmonic oscillator? Now, a mass spring system is a perfect simple harmonic oscillator. Okay? This, however, is not, because restoring force is gravity, and gravity only acts downward. not towards equilibrium.
So I was gonna ask you about that when you were looking at the pendulum.
Mhm.
Like, I don't understand how the acceleration can be 0. It's technically still moving. Or still
It is, but the linear acceleration is 0. See, if it's swinging and moving this way, it still has part of the gravity. It has part of its acceleration is going in the x direction, isn't it? And part of it's going in the y. All right, amplitude. What is amplitude?
Like how high it gets.
Yep, that's this part right here. This is big A for amplitude. It is its distance from max displacement. Amplitude is big A, okay? Period is big T, that weird T. It is the time for what? One what? Yep, we call that one complete cycle. It is in seconds or hertz, isn't it? What's amplitude going to be in? What's the units for amplitude?
Amps?
Meters. Isn't it distance?
I'm thinking of something else.
Yeah. A is in meters, okay? Frequency. Frequency is, yeah, it's little f. You are correct. It is little f. It's that scripty f. It is 1 over period. Technically, we describe this as cycles per second. Think about it. It's how often it returns back over a certain period of time to its beginning place. Think about frequency is your pitch in music. And if you've ever seen a metronome, how do we change the count for a metronome? How do we change the pitch of something? It's the same thing. We slide that little... Do you realize a metronome is a pendulum? It's just an upside down pendulum, isn't it? Instead of going this way, it's going this way. And the weight causes it to do that back and forth. There's a spring inside that causes it to go back and forth depending on how you move that weight. If the further up you go, the longer it gets, isn't it? Further down you get, it's shorter. Okay? And that beats is a frequency, but it's also the pitch of your voice. If you ever put your hand on your throat and you say things higher or say things lower, if you say things lower as your voice gets lower, those vibrations are slower. They're less cycles. Your vocal cords are muscles. They're actually cords they're muscles that are stretched tight and air blows across them, vibrating them. How frequently they vibrate causes the pitch of your voice. Women's are usually shorter than men's. If you look at men's necks on average, they're usually longer than women's. But that's part of it. And you also have Adam's apples, which we don't have. You've got bigger chambers there, which causes more air to blow across, which also causes you to be able to be louder a lot of the times than women. But believe it or not, I know you don't think that, but it's true. So, all right. But if you want, that's what we tell kids also. That's why we tell kids when you whisper, you can't feel those vibrations. That would be amplitude. Amplitude is how soft or how loud. So if you ever want to teach a kid to whisper, you tell them to talk low enough until they can't feel their throat vibrate. That's how you teach kids to whisper, actually whisper. All right, so a mass vibrating at the end of a spring undergoes simple harmonic motion, doesn't it? The restoring force is given by, remember Hooke's law? Hooke's law is F equals negative kx. Yeah, that's also on your formula sheet, isn't it? So remember what happens. It wants to go back to equilibrium. We pull it away. Equilibrium is the middle point that if you let go, it would eventually just rest there, wouldn't it?
Yes.
So we pull it back some distance x, displacement x from there. We've got the spring constant K. You remember we found that, didn't we? In a couple instances, we found spring constant K. That is the stiffness. And think about this. The higher the K is, the harder it is to pull the spring. Slinkies are easy to pull, but if you take a spring for like a gate, you can't make that thing move, can you? That's because it has a very high spring constant, very high tension in that spring. It resists stretching. So it takes a lot more force to get it to stretch. Get it?
Yep.
A high K means a big F. All right. So what is the period of a mass spring system? We've got certain things we need to talk about. We've got X. X, of course, is our displacement. K is our what? Spring constant. And F is the force. To bring the what? Mass back to what?
Equilibrium.
And F always points towards what?
Equilibrium.
Yes. That's why it's negative kx, because it's always opposite the motion of the spring. Okay? The way we're pulling it out. F and X always have opposite signs. If we pull it to the right, the restoring force is to the left. If we pull it to the left, the restoring force is to the... Okay. All right. What is F at equilibrium?
0.
0, because we don't need any force to get it back to equilibrium, do we? So F at equilibrium is 0. All right. So what is the period of a mass spring system? Look on your formula sheet. You will see the period is a version of, it's still 2 pi because it's still cyclical. The 2 pi is part of the cyclical, but instead of L over G, because G doesn't mean anything, and there is no L, is there? What does make a difference in a spring system? The spring constant and the mass. So instead of L over G, it's M over K. The spring constant acts like gravity, and the mass acts like the length of the string in the pendulum. That's that relationship between them, okay? Now, period is proportional to mass. And period is proportional to 1 over K, isn't it? The stiffer the spring, in other words, the bigger K gets, what happens to the period? If K gets bigger, the period goes down, doesn't it? Think about why that is. If you've got a really stiff spring and you try to pull it out, and you get it pulled out, it immediately wants to snap very quickly back to equilibrium, doesn't it? So that totally makes sense that as the stiffer the spring is, the less time it takes for it to go back to equilibrium. A really loose spring takes a lot more time, doesn't it? Because it doesn't take as much energy, right? Not as much force is needed. It's all the time in the world. So what's the equation of oscillation? There is a linear equation here, x of t. It has to do with time. It is, remember what I said about waves? This is a vibration, isn't it? You can feel it vibrate. If you were in pre-cal, you know we talked about these when we looked at sine and cosine. It is a cosine wave. It is A, guess what the A is? Amplitude, that's how big it's going to be, times the cosine of omega t plus phi. Now, this right here is our displacement at time t. This is our amplitude. And this guy right here, omega, has to do with the period. Omega is actually 2 pi divided by the period. Okay? This little guy right here, you don't have to worry about too much. This is what we call a phase constant. In other words, it talks about how much out of position it is when we first pull it back. Okay? That has to do with the position, initial position. All right? We have 2 types of positions we're interested in. Can you guess what 2 positions we're interested in?
Max.
Yep, max displacement and equilibrium. So let's look at this. Because guess what we have again? We have another one of these charts, don't we? We ought to be able to fill these in really easily. So what is the displacement at t equals 0? Max, yep. Max to the right. Which means the velocity is 0. Acceleration is, yep, max to the left. Force is, yep, max to left. Kinetic energy, remember these go together, don't they? Potential energy is max. Now this is u sub s, which is 1/2 kx squared this time, isn't it? So can you finish filling this in? What happens at t to the 4th? We're now at what? Yep, displacement is 0 because we're at equilibrium. So the velocity is what? Max to the left. Which means that the acceleration is 0. Which means that the force is 0 because the force F equals ma, right? Kinetic energy. Yep, max. And potential energy, 0. Now we're on the other side of equilibrium. This position right here, this position right here is equilibrium, isn't it? All right, so now we're past equilibrium, which means we're now where? Yep, max to the left, which means my velocity is 0, right? Comes to a stop, which means my acceleration is now what? Max to the right, because it slowed it down. Force is? Yep, because these go together, don't they? Kinetic energy, though? If the velocity is 0, the kinetic energy is 0. But the spring potential energy is max. All right. Now we're back to what? So displacement is 0.
Max to right.
Yep.
0.
Max to the right. 0, 0, max and 0. And then finally we're back where we started, which means what?
Max to the right.
Yep.
0 velocity. Max to the left for acceleration and force. 0.
Max to the left. Max left. 0 and max. In other words, these are the same, aren't they? Okay, so let's use our formula that we have for this. And figure out what we got going on here. Let's look at example B. It says we have a 7 kilogram mass stretches the spring 0.6 meters. Find the spring constant. Do we know the force? Nope. We can't use F equals negative kx. What can we use? What do we know? It stretched the spring and we've stopped it. What can we use? Mass and displacement. Okay, so we can use energy. You got 3 choices here, guys. You've got Newton's forces, you've got energy, or you've got simple harmonic motion formulas, right? Can't use simple harmonic motion formulas. We're looking for spring constant K. We don't know the period, but what we do know is we know its displacement and its mass. That to me sounds like what? Are you on your phone? Get off your phone. Sounds like energy to me, doesn't it? ME initial equals ME final, doesn't it? What's the initial maximum energy if we've pulled it? Pulled it out here and held it. So what do we have? Spring potential. And now as it's moving through equilibrium, what do we know? It's going to all kinetic, yes.
What?
Uh-oh. We got a problem, don't we?
We don't know.
Crap, we don't know it, do we? Well, phooey. Maybe we don't think about this horizontally. Does this have to be horizontal? Did it say it's horizontal? Just says a mass stretches a spring. So can it be horizontal?
Sure.
But it could also be what? Ooh. Because we're stuck here because I don't know velocity, do I? Okay, so that's not going to work. So we got to think about it this way. Why is this going to work?
Gravity.
Gravity. So we can use Kx, can't we? So if you do the free body diagram here, what do we know is going down? What's going up? Tension, spring tension, which is what? Kx. Okay, so we can do Kx equals mg. Do I have m? Do I have g? Do I have x? And I got k. Mg divided by x, which is the mass, which is 7, times 10 divided by 0.6 gives me a spring constant of what?
116.7.
Okay, so what would that be? What is mg? What units are for mg?
Kilograms in newtons.
Yeah, mg is energy, isn't it? Force, which is newtons. It's force, which is newtons, and then x is what? So this would be newtons per meter. Okay, so we got spring constant. Now it says, what's the frequency in which it vibrates? Okay, so frequency is equal to 1 over what? 1 over t. Okay, so we know what t is, right? 2 pi times the square root of m over k. So this is 2 pi times the square root of what? 7 divided by 116.7. Well, let's figure out what that is. I get 1.54. Did you guys get 1.54?
Yep.
Seconds. Now we need to take and find the frequency, which would be in the 1 divided by 1.54. 0.65. So 0.65 what? Hertz. The nice thing about simple harmonic motion is there aren't that many formulas you can use. There's just a few, and they're pretty much all on this formula sheet, aren't they? That's kind of nice. All right, so let's look at next one. Example C, a spring with constant K equals, oh, they gave us a spring constant. Gave us a mass. Brought to a position, oop, they gave us a position from equilibrium and released and allowed to oscillate on a frictionless surface. So that's nice. Means we don't have to count for friction, does it? Draw the free body diagram of the block. What would the free body diagram of the block look like? There's no tension. So if we do the free body diagram, we have mg going this way. We have what going this way?
That
Normal force. And then what's going back towards the equilibrium position? What do we call that? The thing that wants to make it go back towards equilibrium? Restoring force. So F sub S for spring force, right? F sub R for restoring force. It says determine the period of the spring block system. Okay. So what's the period going to be?
2 pi times the square root of m over k.
Okay, m over k, right? So 2 pi square root of m, which is 0.25, k, which is 40, and you got what?
0.5.
Okay, 0.5 seconds. Now, how do we find the max speed of the block? The max speed of the block is going to be the max what?
It's going to be around the equilibrium.
Max velocity, which is max kinetic energy. And where the kinetic energy is at a maximum, the...
Potential energy is 0.
Yeah. Or it has to be equal to what the potential energy would be when it's at its max, right? So we know that, what? K max has to be equal to U sub S max? Well, what is K max? 1/2 mv squared, and this is 1/2 kx squared. Halves go away, that's nice. We know the mass is what? Yep. K is 40, and the displacement is 0.2 squared. So can you find the velocity? Good. Divide and take the square root. You should get a lovely number. About 2.5, right? Now it says derive an expression for the displacement of the block as a function of time. Well, we know x of t is equal to what? A cosine of omega t plus phi. Well, unless it tells you you've got a phase displacement, the phi goes away. Now, can we find omega to plug in? Can we find A? What is A going to represent? The maximum displacement. A is the max displacement, okay? So this is going to be x max. So we have x of t. What is the maximum displacement here, guys? So 0.2 cosine of omega, which we need. What did we say the formula for omega was? 2 pi over what? Period. Didn't we find the period? 2 pi divided by 0.5, which is what? 4 pi? If we take 2 pi and divide it by 0.5, we get 4 pi, don't we? So this becomes 4 pi t. There is our formula. Okay? Now it says draw the graph. What is it going to look like? What is displacement, velocity, and acceleration of the block over time? Using this formula, what's it going to look like? In general, what's it going to look like? It's going to start, so let's do displacement over time. Let's do x, all right, actually, let's do x over time. It starts where? pulled it back, it starts positive, doesn't it? So it's going to start at some X max, isn't it? It's going to go to where? 0. Now, why am I making it curve? Because it's cosine too, isn't it? Think about it. Cosine means, and he's right, it's not instant. It's not linear anymore, is it? It's not like pendulum. It's a curve because the closer it gets, the faster it wants to displace and then go back out again. Eventually, it goes down to X max again, doesn't it? Negative X max. So it's going to eventually go down to here. How's that? So it's going to want to go from here to here. And then guess what it's going to want to do? Go back to there again, won't it? It's going to look like a cosine wave. Doesn't that look like cosine to you? So this is equilibrium, isn't it? Is that equilibrium? Where's equilibrium? At 0. So equilibrium is where? Equilibrium is here and here. So now, that's displacement. Now let's talk about velocity over time. What did we learn about the velocity? If we pull it back, what does the velocity start at? 0. And then it gets, if it's moving to the right, the velocity is moving to the, or it's moving to the left. We pulled it back, it's moving to the left, isn't it? Left is negative until it hits what? What's its velocity at equilibrium? We're going to do this. Yeah. Do you see why I'm doing this? Because they're parallels here, aren't there, at those points? So it's going to hit its maximum negative at equilibrium. Then it's going to go back to 0. And it's going to hit its what? Yep. Oh, we need one more. Going to go back to positive, isn't it? And then it's going to go back to 0. Look what that looks like again, though. Instead of looking like cosine, what does it look like? Sine this time, doesn't it? Which is the derivative of cosine. Now, let's do acceleration over time for those same points. Let me get my little guy drawn right here. What did we say the acceleration was at? If the velocity is 0, the acceleration, the force is wanting to make it go the other way, isn't it? So the acceleration is actually going to start negative. What did we say the acceleration was at equilibrium? 0. And then it's going to change, then it's going to go back to a positive because it's going the opposite direction. Back to 0 and then down negative again. Now it looks like cosine again, doesn't it? Only flipped over, right? Do you see this relationship? It makes sense if you think about it, doesn't it? Now let's plot the potential kinetic energy. Let's look at the potential energy. We'll do the potential energy in blue. Potential energy for the spring starts high, doesn't it? Wouldn't this be U max? So it's going to start here. At equilibrium, the spring potential energy goes where? Goes to 0. Then it goes where? Back up. Then it goes to 0 and back up again. Do you see that? Does the spring potential energy ever go negative? No. Does the kinetic energy ever go negative? No, it's squared on both cases, isn't it? So if U is positive, I'm going to do K in green. If U starts at a max, where does K start? 0. And then goes to a what? Oh, then goes to where? Max, back to 0, back to a max, back to 0. So look what's happening here. So this is kinetic, and the blue is potential. Does that make sense to you? They both also still look like sine and cosine waves, don't they? There's this wave, the circular wave method that's happening here. All right, so does everybody understand this relationship between the two? And why these guys went above and below, but this guy all stayed positive? Now let's talk about what happens if springs, because we got springs, we can have one spring, can't we? Whenever springs are in parallel, total force is what? Sum of the two. So think about why that is. If we're pulling by 2 springs, isn't there twice as much force happening? So if they are in parallel, spring constant, K total, is K of the first one plus K of the second one. However, it doesn't work that way if they are in series. In other words, they're attached to each other. If they are in series, the effective spring constant is smaller than either of the springs. I want you to think about why that is. We're making it longer, we're making it springier, aren't we? If we're attaching 2 different springs together in series, we're really having to. So what we do is it's the reciprocal of this upper equation. Instead of K equaling K sub 1 plus K sub 2, it's 1 over K total equals 1 over K sub 1 plus, yeah. Think about why that is. It says smaller than either because each spring stretches what? Less, doesn't it? These both stretch the same amount, so we're just adding it in. It's making it harder to stretch it, which means that the total went up, whereas here, each one of them doesn't have to stretch as much, so it actually goes down, doesn't it? It makes sense if you think about it. Yeah, springs in series are less stiff. Springs in parallel, more stiff. Springs in series, less stiff overall. Okay? Totally makes sense if you get it. Example E. We are almost done here.
Is the homework 1 through 11?
Yes, homework is 1 through 11. It's not going to be bad. And the next time we're going to dig into some AP style. So let's finish this up. Example E. 2 identical springs. Strings? Springs. Why did I say springs? I think they meant springs, not strings. Are hung from a horizontal support as shown. So these are in what? Parallel. A block of mass 5 kilograms is suspended from the pair of springs. When the block is in equilibrium, each spring stretches 10 centimeters. What's the force constant of each spring? So what do we know? K total equals what? Yep, K sub 1 plus K sub 2. All right. Which means they're both the same. They're identical springs, aren't they? So couldn't we say this is just K plus K, which is what? 2K. So now we know force, spring force is equal to what? KX, right? Typically. But in this case, instead of KX, what are we going to replace it with? Yeah, 2KX. Now, if it's hanging, it's gravity. Spring force is equal to what? So we replace this with mg, and we've got 2k times however much they stretch. Now here's my question. Do we put in 0.1 or do we put in 0.2? 0.1, right? Because they're not both stretching separately. They're both stretching the next to each other the same amount, aren't they? So it's just 0.1. And then mg, so we have a mass of, what's the mass though? Be careful. Yes, 5. Gravity is 10. 2k times 0.1. Can we solve for k now?
250 meters.
Newtons per meter. Newton meters would be joules. It's not energy, it's newtons per meter. Are we good? All right. We are going to skip this last example F for now because we have not gotten into rotational inertia yet. So we are done for today. We'll come back to this example later.
Did we really need to do this on like notes, please?
Yes, I wanted you to watch it first along with what you just watched. You had just done the spring and the pendulum lab. I kind of wanted to reinforce what you'd seen there. And if you have to admit, it did. So I will check your homework, which was your notes. I'm even going to be nice to you since I wasn't here and ask you, did you do your notes?
Well, technically, yes.
Sam, did you do your notes? Good. Michelle? All right, Sam. Look at you showing me and everything. You're like, yes, I did. Thank you very much. Good for you. Kinley?
Yes.
Caden?
Actually, can I use my ball ice and drops?
Jaden? Nanny? Look at you. You did them. Emma did hers because she said she hated them. I know Jalen did. Colby? Good. Ruben? All right. You've got to try these on your own, right? See what you can do with them? All right. I hope simple harmonic motion seems a lot easier than some of the stuff we've been doing up to this point. It's actually, believe it or not, a difficult concept. Y'all just got to be a lot better at it. Trust me, you're making progress. I'm so proud of all of you.
Have a good day.
You too.
Scared last